What is the S-plane in control system transfer functions? Imagine you have a control system and want to understand how it behaves over time. The S-plane is a powerful tool that helps you see that behavior clearly. It is a graph used in control systems and signal processing to analyze transfer functions. Transfer functions tell us how an input signal turns into an output in a system. They are written in the Laplace transform domain, which simplifies the math involved. The variable in the transfer function is called S, a complex number. This complex number S is made up of two parts, the real part, called sigma, and the imaginary part, called j omega. The real part indicates exponential growth or decay, while the imaginary part relates to oscillations or vibrations. On the S-plane, the horizontal line is called the real axis. It shows how fast the system's response decays or grows. If the poles of the transfer function are on the left side of the plane, the system is stable. That means it settles down over time. If the poles are on the right side, the system is unstable and response grows without bound. Poles on the imaginary axis mean the system oscillates forever without damping. The imaginary part of S, called omega, determines the frequency of these oscillations. Poles are specific points where the transfer function becomes infinite because the denominator is zero. They are marked as x on the S-plane. Zeros are points where the transfer function becomes zero, marked as O. The location of these poles and zeros affects how the system responds. For example, poles close to the imaginary axis cause slow decay or sustained oscillations. Poles far to the left lead to quick settling times. Complex conjugate poles in the left half-plane create damped oscillations, with the real part showing how fast the oscillations die out. The S-plane helps engineers visualize how a system will behave in the real world. By looking at pole locations, they can predict if a system will be stable or not. They can also design controllers to move the poles to desired spots for better performance. When poles are in the left half-plane, the system naturally responds in a controlled way. If they are in the right half-plane, adjustments are needed to prevent instability. In electrical engineering, the S-plane is used to analyze and design circuits, filters, and feedback systems. It simplifies complex differential equations into easier algebraic forms. This makes it easier to see how changes in the system affect stability and response. The S-plane is like a map that shows the system's natural tendencies. It helps engineers decide where to place poles to get the response they want. Whether it is reducing overshoot, speeding up response, or ensuring stability, the S-plane provides a clear visual guide. In summary, the S-plane is a key concept in control systems. It maps the complex variable S to help us understand how systems behave over time. By analyzing the poles and zeros on this plane, engineers can determine if a system is stable, how it responds to inputs, and how to improve its performance. It turns complicated math into a visual picture that guides system design and analysis.